Hi, hello, welcome back. Our next topic is propagation of sound. We have seen that sound is produced by the vibrations in an object. Sound energy is propagated as a wave. In a wave motion, vibrations starting from the sound source are transmitted from one point to the next and so on. These vibrations travel in all directions through the medium particles. When these vibrations reach your eardrum, you perceive the sound. So, a material medium, solid or liquid or gas, is necessary for the propagation of sound from one place to another. In other words, sound cannot travel through vacuum. That is very important how the propagation of sound happens. Okay, we all know that the sound is produced by the vibration of the object, and the sound waves are propagated, or sound energy are propagated in the form of waves. Okay, so it is propagating from one point to another point in the form of waves. Okay, so whenever the vibrations reaches your eardrum, then you will perceive the sound. Okay, the important thing is that a material medium, whether it is a solid or a liquid or a gas, is very important in order to propagate the sound. Okay, so we can say that, or we can say in other words like sound cannot travel through vacuum. So in order to prove that sound cannot travel through vacuum, we can perform the following experiment. Experiment to demonstrate that sound cannot travel through vacuum. Experimental arrangements: a bell jar, a vacuum pump, an electric bell, a battery, a key, and a stopper and a switch. Procedure: take a bell jar and fit a vacuum pump to it. Suspend an electric bell inside the jar and connect its ends to a battery and a key. Seal the mouth of the bell jar by a stopper. Switch on the key so that the current begins to flow. You will hear the bell ringing. Now pump out all the air from the jar using a vacuum pump. Say this experiment is done as two cases. Okay, in the first one, we are arranging all the materials as like the figure shown. Okay, and after that, we are switching on the key and the bell begins to ring. Okay, in that particular time, we can hear the bell ringing. Okay, that is the first case. And in the next case, we are pumping out all the air from the jar using a vacuum pump. Okay, slowly we are pumping out all the air. Okay, so what will you hear? As the air is gradually pumped out, the sound gets fainter and fainter, and finally you do not hear any sound. So you can see that the bell is ringing. See, we are pumping out all the air from the bell jar using a vacuum pump, so that the sound of the bell ringing will be fainter and fainter. And after that, what happened? Finally, we didn't hear any sound even though the bell is ringing. Okay, so this shows that a material medium, so inside the bell jar there is air in the first case, so that we can hear the sound. But in the second case, we are pumping out all the air. Okay, so there will be no medium inside the bell jar, so that we cannot hear the bell ringing. So this experiment shows that, or we can conclude that, the sound requires a material medium for its propagation and cannot travel through vacuum. Vacuum means nothing inside. Okay, there will be no medium. Okay, so sound requires a material medium in order to propagate from one place to another. Sound can travel through air medium in all directions. This is clearly ascertained from the fact that we are hearing all the sounds produced around us. We can perform a simple activity to show that the sound travels through air in all directions. To show that sound travels through air in all direction, ask one of your friend to produce a loud sound by blowing a whistle. You can understood and it is very familiar to you when we are asking any of your friend to whistle, okay, or a bell ringing, we can hear the sound. It is because air is all around us, okay, and the sound source, when it is producing sound, it will be propagated from that sound source and it is reaching our eardrum in the form of waves. So the air or the we can hear, or the sound of a whistle or a bell is heard by you in all directions. So this shows that the sound travels through air in all directions. Okay. Next one is to show that sound travels through gases. The materials required are a balloon. Take a balloon filled with air and press it to your ear. Gently scratch the other side of the balloon with your fingers. Thus, the sound of scratching reaches your ears. Of course, yes, this activity shows that the sound travels through gases. It is also a familiar activity that you have to take a balloon and it will be blown with your with air, and we are keeping the balloon to your ears. Okay, on the other side you just scratch the balloon using your fingers. Okay, we can hear the sound of scratching the balloon from the other end. So this shows that the sound can travel through gases. Okay, and the next activity show that the sound travels through liquids. For that we are taking a bucket, water and a key bunch. And the procedure is like this: take a bucket full of water and a key bunch having at least 3 or 4 keys in it. Put your ears just touching the water level in the bucket. Put the key bunch into water holding in your hand. Now gently shake the key bunch inside water, but it should not touch the side or bottom of the bucket. You can hear the sound of the key. Is it louder and clear? Yes, we hear the sound clearly. Thus, we conclude that the sound travels through liquids. When we are taking a bucket full of water and we are keeping a bunch of keys and we are shaking it inside the water, we can of course hear the sound. So all these activities shows that the sound can travel through solids, the sound can travel through liquids, gases and air. Okay, next activity is that in order that sound can travel through solid. A wristwatch or an alarm clock, a long wooden table or a bench. This is very familiar. No need to take all these materials. If you are just keeping your ears on the bench, wooden bench, and you just scratch or make a sound from the other end of the bench, of course you will hear the sound. Okay, so all these activities shows that the sound propagates or travels through solid, liquid, gas and air. So sound always requires a material medium in order to propagate from one place to another place. Okay. Next one is sound as a longitudinal wave. We now know that sound is a form of energy and is produced due to vibrations in the source of sound. When an object vibrates, it possesses kinetic energy as well as potential energy. During its to and fro vibration, a material particle collides with the neighboring particles at rest, and in the process it transfers some energy to that particle at rest. As a result, that particle also starts vibrating. In turn, it may transfer energy to the next neighboring particle and so on. In this manner, sound energy spread throughout the medium and reaches the ear of the listener. This method of propagation of energy is known as the wave motion. Okay? Thus, wave motion is the motion of sound energy through a medium due to the to and fro vibration of medium particles about their respective mean positions. In a wave motion, medium particles do not move permanently from their respective positions, but the energy moves forward. Okay, so here they are telling us that sound as a longitudinal wave. We all know that sound is produced by the vibration of the object. And while vibration or during vibration, we all know that it will possess both kinetic energy as well as potential energy. Okay, so during its to and fro motion, the medium particles collide with each other, that is to the neighboring particle, and they are transferring some of the energy to the particles. And this process is continuing, okay, till till the wave reaches the ears. Okay, so this is how the wave motions are happening. So we can say that wave motion is the motion of sound energy through a medium due to the to and fro motion or vibration of the medium particles about their respective mean positions. Okay, so we can say that sound as a longitudinal wave, that is, the sound is propagating as a longitudinal wave. In a longitudinal wave, alternate regions of compressions and rarefactions are formed. Compressions are the regions where medium particles are crowded together and medium density is high. And rarefactions are the regions where medium particles are spread apart and medium density is low. Okay, so we can say that the longitudinal waves is a combination of compressions and rarefactions. Rarefactions or the compressions are the region in which the medium particles are crowded to each other. You can see in the picture, that is in the B section, you can see the medium particles are crowded. Okay, and so the density will be higher in that particular region. So that is known as compressions. Okay, the region in which the medium particles are crowded and the density is high is known as compressions. And the region in which the medium particles are apart, spread apart, and the density is low, they are known as, or that particular region of the wave is known as rarefactions. Okay, so here is a longitudinal wave in a slinky. Okay, so the longitudinal wave is the alternate combination of compressions and rarefactions. Okay. Next one is the graphical representation of a longitudinal wave. Direction of sound wave propagation, that is figure 6.9 clearly shows that the graphical representation of a longitudinal wave. A longitudinal sound wave is graphically represented as shown in the figure 6.9. Here the direction of propagation of sound wave is taken along x-axis and the density of air medium is taken along y-axis. Points C1, C2, C3 represent compressions that are the regions of high density. On the other hand, the points R1, R2, etc. represents the rarefactions, that the region of low density. One wave consists of one zone of compression and one zone of rarefaction. Okay. See in the picture, it is clear that in the x-axis the direction of sound wave propagation is given, and in the y-axis the density of the air medium is given. Okay. So a longitudinal wave is represented like this, and the points C1, C2 and C3 are the region where the medium particles are crowded and the more density. Okay, so that particular region are known as compressions, and the points R1, R2, etc. are rarefactions, in which the region in which the medium particles are spread throughout and the density becomes low. Okay, so this is how we can represent a sound wave graphically. Okay. Next one is some terms related to a wave. Following terms are important for the description of a sound wave as follows. How we can describe a wave motion. So first one is that vibration. The to and fro motion of a medium particle once around its mean position is called one vibration. Thus, in one complete vibration, a medium particle moves from its mean position to one extreme position, then to the other extreme position, and finally back to its main position. Okay, so this is known as vibration. Okay, that is the to and fro motion of the wave from its mean position. Okay, that is known as vibration. That is, the wave is starting from the mean position and reaching an extreme position in the upper side, and again coming back to a lower position, lower extreme, and moving back to the mean position itself. Okay, so one complete vibration consists of one compression and one rarefaction. Okay, next one is amplitude. The maximum displacement of a vibrating particle on either side of its mean position is known as the amplitude of the wave. It is denoted by the symbol A. Okay, so the amplitude is, you can see in the picture, that is the maximum displacement from the mean position, okay, to one extreme point is known as amplitude. Okay, it is represented by the symbol A. And time period, it is the time taken by a vibrating particle to complete one vibration to and fro about its mean position. It is denoted by the symbol T, and its SI unit is second. Okay, that is, the time required to complete one vibration is known as time period. Okay, and next one is frequency. The number of vibrations completed by a vibrating particle in unit time is known as its frequency. It is denoted by the symbol nu. Okay, see, next one is frequency. That is, frequency is that number of vibrations. Okay, number of vibration per second. How many vibrations taking place per second? It is the frequency of the wave, and it is represented by the symbol nu. Okay, the SI unit of frequency is hertz, where one vibration per second is called 1 hertz. If an object vibrates with a particular frequency, then the sound produced due to its vibration also have the same frequency. The frequency of vibration is the reciprocal of its time period. That is very important. That is, frequency will be the reciprocal of the time period. So we can represent it as nu is equal to 1 by T. T is the time period. That is capital letter T. And its SI unit is second. Okay. And we can also write like this. Time period T will be equal to 1 by nu, which is the reciprocal of the frequency. Okay. The last term is that wavelength. One wave is said to be completed when a medium particle completes one vibration about its mean position. The length of one wave is known as the wavelength of a given wave. It is usually denoted by the symbol lambda. Its SI unit is meter. Okay. See, it is the distance between two compressions or two rarefactions. Okay, that is known as wavelength. Okay, so R1, R2, that is wavelength. C1, C2. Okay, the points, we can say that C1 and C2 is the lambda or wavelength. That is the distance between two compressions or two rarefactions. Okay. So these are the important terms related to a wave. So this is for this class. Everyone go through the textbook, read all the concepts and understand the concepts. Then study nicely, keep watching, keep safe in your home. Thank you.